Hello everyone and welcome to your 511-1 practice exam question. Today we have thermochemistry, so enthalpy, entropy, and Gibbs free energy. Beginning with enthalpy, which is heat change or thermodynamic stability. A reaction that releases heat is exothermic, one that takes in heat is endothermic. And enthalpy is subject to Hess's law, meaning we can add together the heats of reactions to get the heat of the entire thing. And that leads us to the ability to find heats based on heats of formation, where the heat of the reaction is equal to the heat of formation of the products minus the heat of formation of the reagents. And finally, we can also use bond enthalpies, where breaking a bond takes energy and making a bond releases energy. Next up we have entropy, which is a measure of chaos, disorder, number of configurations, and any other general term for how much of a mess the system is. Entropy is very similar to enthalpy in terms of its manipulation, so we can add together entropies of reactions to get the entropy of the total reaction, and we can use entropies of formation, so reaction equals products minus reagents and all that good stuff. Additionally, we can use our intuition to tell us something about the signs and the rough magnitude of entropies in general. So gases are more chaotic than liquids are more chaotic than solids. Also, bigger molecules with more degrees of freedom or more jiggly parts are going to be subject to having larger amounts of entropy. Finally, we have Gibbs free energy, which is a measure of the spontaneity of the reaction. So a negative free energy means your reaction is spontaneous, it's going to run, whereas a positive free energy means it's non-spontaneous and is not going to run. We can do all of the usual manipulation, free energies of formation, reaction equals products minus reagent, and all the usual. Additionally, we have the interesting equation of delta G equals delta H minus T delta S, which means that our free energy can be determined from the enthalpy, entropy, and the temperature. Now let's consider NO2, which is reddish-brown poison. It's formed through the reaction of NO with oxygen. And we want to know at what temperature we would have to have our system or our world be for this reaction that forms reddish-brown poison to no longer be spontaneous, which would be kind of nice. So first we want to calculate the enthalpy given our enthalpies of formation. So our overall enthalpy of the reaction will be the enthalpy of the products minus the enthalpy of the reagents, remembering that they all have coefficients of 2, so we need to keep those coefficients in there. And when we do out the math, we get that the enthalpy is decreasing, which is favorable for spontaneity, by 114 kilojoules per mole. We do basically the exact same process for the entropy, so products minus reagents with the coefficients in there. This time our oxygen does not have an entropy of 0, so we have to include that. And we find out that our entropy is also decreasing, which is not favorable this time, by 146 joules per Kelvin mole, which we put into kilojoules for our convenience in the next section. Now we want to use our equation of delta G equals delta H minus T delta S, noticing that we have opposite effects, so at high temperatures the entropy will be more important, and at low temperatures the enthalpy will be more important, so whichever one wins will determine the spontaneity of the reaction, and the changeover will occur for the temperature for which our delta G is equal to 0. So we take our equation, we set it equal to 0, we solve for our temperature, and when we plug in the numbers, we notice that the temperature of the switchover is 779 Kelvin, which is quite warm, so the odds of us getting to a temperature where this changeover occurs and we're not making reddish-brown poison are pretty slim, so we should probably avoid starting with NO in the first place. For the next part of the question, we're given some thermodynamic information. So we're given a reaction of oxygen atoms to form O2 and its enthalpy. And we're also given the enthalpy of formation for ozone. And what we want to know is what is the bond enthalpy of each of the two oxygen-oxygen bonds in ozone. So this is a Hess's law problem. We're given two reactions, and we're asked about the enthalpy involved in a third. So what we want to do is we want to get these reactions into a good form. So that means in our case of oxygen going to O2, we want to scale it so that it's going in the right direction and so that it has the coefficients that he likes. So we flip it around and we multiply it by 3/2 and we get a new enthalpy there. Furthermore, we have the heat of formation of ozone, which was given, and that reaction that goes with that is 3/2 O2 goes to O3. And we can flip it around and also flip the sign of it so that it's ready to use in Hess's law. We can add up our reaction and our enthalpies to get the enthalpy of O3 going to 3 oxygen atoms. And we can say that breaking each of the two bonds took half of that total enthalpy, so we get a bond enthalpy of 302 kilojoules per mole. Now for the next part of the problem, we're given a molecule that has two isomers, so two arrangements, A and B. And the B isomer is more flexible, has more states available, which you can see on the drawing. It has more levels, and what that means is it has more entropy. And we're asked to consider cases where the enthalpy might favor A or it might favor B. So we'll consider that case first, the case in the drawing. So we want to know which isomer is favored at low temperature. When the temperature is low, the entropy term isn't that important, so the enthalpy term is important. So we want the thing with the deeper well, so A is favored. At high temperature, the entropy is the thing that we care about, so we want the thing with more ledges, more levels, so we want B. Now, in parts 3 and 4, they get a little bit tricky, so they ask us to consider a case where B's well is actually deeper. And in that case, B will have lower enthalpy, and it will be favored when enthalpy is important, so at low temperature. But B still has the same higher number of ledges. That hasn't changed. So it's favored at high temperature as well. B is now favored all of the time if it has the deeper well, the lower enthalpy. And then finally at the end it asks us a quick question about what the sign is for the reaction A to B entropy term. So B has more chaos, more ledges in all of the examples in this problem. So going from A to B increases the chaos, it increases the entropy. And that's it for today. Be sure to catch the rest of the practice videos and good luck on the test.